Okay. So first of all, thank you very much for having me. I want to thank Samuel and the whole of Keen Lab for inviting me to this awesome conference. It's my second year in a row, and it's really nice to see the conference grown bigger with a greater lineup, nicer venue, I would say. So yeah, thank you very much, and I hope to come back next year. All right, so what am I going to talk about today is a story about our entry at Pwnie, mobile Pwnie last year. We popped a couple of devices. One of them is the Samsung S8, and the other one was Huawei Mate 9 Pro. This time I'm going to talk about the Samsung S8 exploit chain. It's kind of a special exploit chain for us because we decided that no matter what kind of bugs we find, we're only going to use logic bugs. And if we find any memory corruptions on the way, we're just going to discard them and keep finding logic bugs until we can construct an entire end-to-end exploit chain entirely made out of logic bugs. And apparently, it was the longest ever submitted exploit chain as part of the competition. I'm sure most of you already know about Pwnie. It's a competition where people turn up and they're given the latest devices, mobile devices, chosen by the vendor, chosen by ZDI, and there are several categories. One of them is the browser category, which is the category we enrolled for, and our target of choice was Samsung Galaxy S8. At this point, it was running Android Nougat, and I'm going to cover some of the details related to this platform, some of the mitigations, and in general, I'm going to try to cover the entire process of finding bugs, circumventing some of those mitigations, finding more bugs, chaining them together, etc. So we've been doing Android mobile Pwnie on Android for quite a while now, and we have developed kind of a special relationship with Samsung to the point where I volunteer for their marketing department to promote the platform as a playground for people interested in starting in Android. It's a great platform to learn and find bugs in. I'm not sure if I would use it as a customer, but if you want to get into Android security, it's a great place to start, really. So how would you approach something like Pwnie? You're given a platform, you're given the scope, where do you start, what kind of stuff you look for? So the most traditional approach would be to look for well-known patterns of code that's been known to be vulnerable and exploitable in the past. Things like unsafe class loading from files on the file system, hash traversals while unzipping an archive, or external storage operations, or some sort of botched SSL error handling. So if you know what you're looking for, you know what it looks like in terms of code, the way to do it is to, I don't know, maybe start grepping for some of those APIs related to those bug classes through the smiley files, and then start confirming if they're accessible, if they're vulnerable, if they're reachable from the attacker's perspective. And you have to repeat that for every application. Now, the Samsung Galaxy is a very clumsy one, and it has something like, I don't know, 200, maybe 300 applications installed on it by default. It's a huge attack surface. So if you just follow this trivial approach, you end up with so much noise that it's not even feasible to find bugs within the time allocated for Pwnie. We mostly do Pwnie in our spare time, which means staying late after work, ordering some pizza, opening Jeb, and cracking on with bug hunting. So it's not really a full-time job for us. So we have to optimize this process. And we try to optimize it without investing too much time into optimization either. We want something really quick and dirty that can get the job done, that will speed up the process, but also not take too much time to develop. So we want to find code patterns that are accessible, reachable, and vulnerable. We want to query the code it is to find those code patterns and confirm some characteristics and aspects for them. So if you've heard of Yearn, it's code property graph database that will consume C or C++ code base. It will apply some fuzzy parsing on it. And then you have the ability to issue queries for the code you're processing. Things like, give me all the instances of memcopy where the size parameter comes out of some mathematical operation applied on an integer, where this integer is different from the one passed to a malloc call before the memcopy is issued. Things like that. So we need something very similar for Android, and the name kind of stuck. It's called Jandroid, and it will parse Smiley files instead of C and C++. So this is roughly how it works. We know what we are looking for, so we start with the search term. The search term is related to one of those bug classes I mentioned before. So in the case of an unsafe unzip, we look for getNextEntry, which is a well-known API call, part of a vulnerable code path pattern related to unsafe unzips. So once we find an instance of this call, we find all of the calls to this particular function, and we apply this recursively. So we end up with a graph where the starting point is some activity, hopefully reachable by the attacker, and the endpoint is the vulnerable code. At the end of this process, once we find all of these calls recursively, we go through the list and we check if any of those activities leading to the vulnerable code are actually exported in the Android applications manifest. This is what it looks like, just roughly. You have the search term, you have the method that calls the vulnerable method, and the method that calls the method that calls the vulnerable method, and eventually, hopefully, you have some activity that's defined in the manifest as both enabled and exported, and obviously browsable if you want to target it from a browser's perspective. This is what it looks like. This is just an example. In this case, it's getNextEntry again. And there are some calls to it, and they end up in an onReceive method, which is a method associated with a broadcast receiver. So this is potentially something you can trigger using a broadcast. To do that, you need to be a local attacker, so that's not interesting to us. There is another one doing background, but neither of those are actually attached to anything exported, enabled, and browsable, defined in the manifest. So when we look for unzip issues, we usually look for calls defined in the Java util zip module, part of the standard JVM. However, Samsung also use a bunch of other libraries and custom implementations for treating zip files. One of them is netlingala zip4j. So if we look for getNextEntry, we won't get any of those hits related to Lingala. Lingala's equivalent would be to search for something like extract_all. And this is what it looks like. So we have the vulnerable code. Once we have identified it, we know what to look for. And we have all the calls and chains of calls leading to the vulnerable code. And at the end of this chain, some of these obviously won't be reachable. So some of these, I hope you can see it, start from an onClick method. And an onClick method is related to user interaction on the screen. So a victim needs to confirm a prompt or click a link or something like that. So unfortunately, that's not in scope for Pontoon, so we look for something else. And this is the interesting bit. So extract_all is called by convert to sdoc something, convert to sdoc something, wrapped again, doing background, run convert, etc., 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 coming to onCreate method for an activity that's defined, exported, enabled, and browsable, hopefully, in the manifest. So if you run the query on an application and you see your vulnerable code reachable from something like that, defined in the manifest, that's how you know you should go through this chain and manually confirm any if statements or conditions that you cannot satisfy as an attacker. But still, this cuts down the amount of code you need to read by a margin. All right, so the previous instance of vulnerable code is actually part of the Samsung Notes application. There is a directory traversal when processing memo files. Memo files are just zip files, actually, with the memo extension. And it's very trivial. If you pass a memo file, you can unzip a file anywhere within the sandbox or on the SD card, because the application has access to the SD card by default. A lot of people ask about Jandroid and whether we're going to release Jandroid or not. Well, the answer is that at this moment, at this stage, the code is not suitable for public consumption unless you want your face to melt while reading the code written by Rob Miller. Right, at the moment, so what we have some Vone, which is writing files by traversing, and we know what we want to achieve, which is code exec and exfiltrating of data. And we know where we start. We start in the browser. This is just scoped by ZDI, saying you open a browser, and that's it. You leave the phone. There is no user interaction. Go get your code exec and exfiltrate some interesting stuff. All right, so Samsung Notes. This is the vulnerable activity. We see that it's exported and enabled, but it's not browsable. This means this is not directly reachable from the browser, and we need some other means of reaching this activity. Fortunately for us, there are some browsable activities that we can abuse to proxy our intent for the vulnerable activity. In this case, Android vending. I'm not entirely sure what the purpose of this application is, but it's something related to the Google Play Store, as far as I can tell. But one of the browsable, exported, and enabled activities in Android vending will take two parameters, URL and ID. It will take those parameters and create an entirely new intent out of it. And it will call the view action on it, which is great. At this point, we can reach something that's not browsable. And how do we do that? So you might think we can do something like market : / details, where URL equals to some memo file, and the ID equals the package name we're attacking, in this case, Samsung Notes. Unfortunately, the manifest is a bit strict on what kind of URLs can be processed by the memo application. So if you specify the URL like this, the package manager will just reject the intent and say, I can't match this intent to any of the intent filters. What you can try instead is pass a file scheme. The problem with the file scheme is that the package manager, once again, won't be able to route the intent to Android app notes, because by passing it with a file scheme, the package manager won't be able to get the right MIME type associated with the intent filter. Also, on Android 7.0 and above, Android, they try to prevent people from passing file schemes around. So the way to do it properly, according to the documentation, is use a content scheme. OK. We can use a content scheme. A content scheme is associated with a content provider. One particular case of a content provider is a file provider. We can use a file provider implemented by Chrome in this case. You can see the definition of the file provider, and you can see that the file provider is mapped to cover the download folder. So if you have a file in the download folder, you have a URL starting with content / that will map to this file. So we can try something like this. We can specify the URL to be content / then we specify the file provider URL and the file name at the end. Now, unfortunately, file providers are a bit tricky because the file provider won't store MIME type information related to this file. What the file provider will do is it will look up the file extension and it will see if this file extension is a well-known extension and then deduce the MIME type based on this MIME type if it's a well-known one. Now, unfortunately, the memo extension is a Samsung proprietary extension, which is not defined. Therefore, this is unresolvable by the package manager. One thing that's a main difference between content providers and file providers is that content providers, unlike file providers, will store information about the MIME type. And the way they do it is by taking that information, let's say, out of a HTTP response. So if we download a file, and in the HTTP response, we specify the MIME type to be, let's say, application/memo, this will be tainted and inserted into this content provider. So something like content : / media external file 350, where 350 corresponds to our file, will be accepted by the package manager. Because when the package manager retrieves this file, it will look up the MIME type that's already stored by the content provider. But what the heck is this 350? Well, that's an ID that's assigned by the content provider to each one of those files that are mapped by the content provider, and they're incremented sequentially. So for every new file you download, the content provider will increment the ID and associate it with the file you just downloaded. But how do we know the ID of a particular file? Well, we can brute force it. If we use a script element and we try to load a file using this script element and the content scheme, we can check the on-error or on-load code callback and know if this file exists or not, or at least know if a file with this ID exists. The issue is we can only do this from a content scheme. And the way we do it, by the way, is going through a bunch of IDs, starting with a high number and decrementing one by one, until we reach one that will fire the onload callback. And that's how we know that's the last ID. So if we're the last person to download a file, we know this is the ID that corresponds to the file we just downloaded. This is what it looks like. So if we're in a browser and we force download a file with an application/memo MIME type, we can use JavaScript to brute force the ID that corresponds to this file in a content provider. However, as I said, this can only work from a content scheme. So if you're in an HTTP scheme and you try this JavaScript snippet, it won't work because of same origin policy. But if you're in a content scheme and you execute the same piece of JavaScript, it will actually work. Now, the content scheme is disabled in the default browser in Samsung, which is S-Browser. But it is implemented by Chrome. So can we find a way to jump from Samsung's default browser to Chrome without any user interaction? And it turns out we can. There is a poorly documented scheme called Google Chrome. We can use this scheme to redirect Samsung browser to Google Chrome. And the URL we pass as a parameter will be the one that will be opened by Chrome. Interestingly enough, this was reported by Takeshi Terada, very smart guy, finding really interesting bugs related to absurd behavior in browsers. So I found the Google Chrome scheme issue, and I was like, OK, that's great. Then someone from the office pointed out this has already been reported. I'm like, OK, bugger. Can't use that for Pontoon, really, because it's not on ODE anymore. Then I scrolled down, and I realized they patched it. And it was still working in my browser. So what was wrong with it? Well, turns out someone else patched Chrome as part of some other bug, and as a side effect, this was patched magically, and they can't be bothered tracking down the root cause of this bug, and they just assumed it was patched. Well, it wasn't really patched. I can't really tell what happened there, but it was still working. There was a CV assigned to it, so I consider it patched. OK, so if we use something like Google Chrome navigating to content:// Chrome blah, 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 payload.html, where payload.html is the file we just downloaded, this works. And we can force the file download using this piece of nginx config. If we do application/force download as a MIME type in S browser, this will be downloaded without any prompt. So this is what it looks like so far. From a Samsung browser, we go to index.html. Index.html forces the Samsung browser to download payload.html. Then we use the Google Chrome scheme to redirect S browser to Chrome. Then from the Chrome application, we use the content scheme brute forcing mechanism to find the ID of payload.html. Once we find the ID of payload.html, we force download another file called whatever.memo. Since we know the ID of payload.html, we now know the ID corresponding to whatever.memo, because this is payload.html ID +1. So once we have that, we trigger the intent proxy bug in Android vending and proxy our request until we reach Samsung nodes. So at this point, we can actually trigger this bug. Great. All right, there is a missing piece in the puzzle. We still don't know what to do with the file write. OK, let me recap. What we have at the moment is a file write within the application sandbox or anywhere on the SD card. How do we turn this into code exec? Two really naive approaches you can think of. Just grateful stuff that will be touching SD card in one way or another, looking for files on the SD card, and change behavior based on a file on the SD card. Way too many false positives, unfortunately. The really naive dynamic approach would be to use iNotify, which is part of the Linux kernel subsystem. And it will help an attacker identify any operations within part of the file system. So if I use iNotify, I can monitor a certain folder on the file system, and every operation, such as open, close, read, write, etc., will be logged by iNotify. So in theory, I can use this to monitor every application that will touch the SD card. Well, yes and no. The way Java works is most of the applications, before operating on a file object, will call .exist on the file object. And the .exist method will return true or false, depending on the file is actually there or not. And the thing is, I have no idea how JVM works. I looked at the code, but I couldn't really understand. It's a very interesting way, but they pre-cache some of the file system structure, so they have knowledge of whether a file exists or not beforehand. And they don't actually result in an iNotify. The .exist calls don't result in touching the file system. So what we can do instead is hooking. But to hook, we need to generate some actual activity. We need to generate some actions on the phone. How do we do that? Well, we have a proxy for bouncing intents off of other activities. We have browsable activities. OK, let's compile a list of everything that we can reach. So we write a short Python script to pass the manifest. We pull out the list of activities that are reachable, which means enabled, exported, browsable, plus the activities that we can reach with the intent proxy. Then we have another Python script that will go and try to identify potential arguments for the intent URL for each one of those activities. It's nothing fancy. It's kind of dirty ghetto grep kind of thing, but it will try to identify arguments that are necessary for the activity to act on the intent. OK, so we have a list of things to go through. We use an ADB shell, shell wrapper for ADB to go through this list and open each one of the activities we have. And we use exposed, in this case, to hook across every single application. I'll show you the script in a bit, but we use exposed for something that we know we really want to achieve, and we use Frida for stuff that we're not really certain what we want to do with them. So we use Frida mostly for reversing purposes and debugging code, and we use exposed when we need early injection point because it injects into Zygote. And this is what a really simple exposed module looks like. In this case, it will hook every single application that's running on the Android phone, and for each one of them, it will act on .exist part of the file object. It will hook them. It will hook every single call to .exist and check if the path starts with storage, SD card, mount, or the location of the application sandbox. If that's the case, we log the attempt. There was a huge list of applications that were touching the SD card for some reason. And one that stands out is Galaxy Apps. It turns out Galaxy Apps, well, for those who don't know, Galaxy Apps is an application. It's Samsung's proprietary Play Store. So Samsung-specific applications, instead of searching for them on the Play Store, you go on Galaxy Store and look for them. But it's a very powerful application. It can install APKs. It can deinstall them. It can play with the cache and things like that. So a very powerful one. It's a good sign for us. And the phone was quite simple. They were looking for a file on the SD card. If this file exists, they'll read the file and reconfigure the entire behavior based on the contents of this file. The file is called saconfig.ini. And it controls every single aspect of the operation of this application. If you read the source and you grep for /SD card or /mount or something like that, you won't really pick this one up because it's, well, how do I call it? Obfuscated. To deobfuscate, you just copy the string out and you call the same method with it outside of the application. It's a very sloppy one. But this translates to saconfig.ini. Some of the parameters that will be read out of the file are related to something called a staging mode flag. If you have the staging mode flag set, it means that you're operating in a developer's network or testing network or something like that. And when you're in staging mode, you can specify your own Galaxy Apps server. So when Galaxy Apps runs in staging mode, and you specify your own staging server, every time it needs to make a decision, it will go to the IP of the staging server you specify. And there's a third one. This one specifies how often Galaxy Apps will check for updates. Pretty interesting. Here is an example config file that we drop on the SD card to see what happens. First, we set the staging mode flag to be on. Then we specify staging server URL, which is our own IP. This could be on a local network, could be on the internet, could be anywhere, really. And then we specify the time about how often Galaxy Apps should check for updates. This is not exactly the value. This value is actually processed further, but this is the value that we need for triggering an interesting integer overflow that I'll mention in a bit. OK. We know about this vuln. It's an awesome vuln. How do we trigger this vuln? Well, it turns out Galaxy Apps will only pick up this file in two cases. First, the app has been just restarted, which is not likely unless you manage to crash it. Second, the phone just rebooted. Well, this is even harder. So 2 scenarios from here. We tried to look for a way to crash Galaxy Apps. Well, couldn't find any. What about rebooting Android from a browser without any user interaction? Is that even a thing? Well, I didn't know until then, but if you manage to crash a system-critical process on Android, the entire phone will reboot. It doesn't matter what kind of crash it is. Even a simple no-pointer dereference that won't affect the operation of the phone will trigger a soft reboot, what they call, if it's not a caught exception. So if they don't catch it, boom. And there's an interesting one in the telecom service, the user call activity, where you call the activity, but you don't provide a URL. If you don't provide a URL, they try to dereference the URI while getting the scheme for it. And if there is no URI, you dereference no. And this results in a no exception. There is no try-catch block around it. So boom, you restart the entire phone. And this is what it looks like in a manifest. It's enabled. It's exported. It's not browsable. OK, how do we do it then? Well, let's use the intent proxy bug from before. We can't, because we cannot specify the activity name explicitly. We can only specify the package name and the URL. And the package manager needs to map those two things to an intent filter. And according to this intent filter, there's no way we can do it. So we look for another intent proxy bug. This one is in Samsung members. This one is a browsable, enabled, exported activity called launcher activity. And this is what it looks like. It will take two arguments, package name and class name. It will take those two arguments and create a new intent from them, and it will send this intent onto the package manager for resolving. All right, this is just a quick recap of what the intent proxy bugs look like and why they're so different. The first one, in Android vending, allows an attacker to specify a package name and a URI. This is what is called an implicit intent. The implicit intent relies on the package manager to look up those two things into a manifest and decide if this intent belongs to the application or not. And if it belongs to the application, package manager needs to resolve the destination activity. The other one in Samsung members, on the other hand, is an explicit intent, because you specify the package name and the activity name. So in this case, package manager doesn't need to make any decisions. It just goes and throws this against the activity you specify. All right, and this is what the Samsung members intent proxy abuse looks like. VOC is the scheme registered by Samsung members. If you pass parameters like package name and class name, it will take them, create a new intent, and pass it on to package manager. Package manager will look up the telecom service manifest and match it against the user call activity because we explicitly specify it. But we don't specify a URL, so the URL is missing. They dereference the URL to get the scheme, and they crash the phone. OK, at this point, we need to automate this in the browser, from a browser perspective. We need 2 clicks, automated clicks in JavaScript to do that. One of them to drop the file in the SD card by triggering the path traversal, and the second one to crash the phone. Well, how do we do that? Every time we do a second automated click, we get a navigation block error in the browser. So we need a way to smuggle this second click. The telecom crash is interesting. While debugging the telecom crash, I realized that there is a time between triggering the bug and actually restarting the phone. And don't ask me why or how this works. I didn't really debug it because I kind of brute forced the combination to smuggle a second click while the phone was crashing. So the Chrome developers were actually puzzled, and they said, you shouldn't really need this at all. This should just work. Anyway, I spent a couple of days working on it, and it wasn't working at all. It wasn't resolving itself, so that's why we had to go and find a bug. Anyway, this is what it looks like. So first, kind of counterintuitive, I guess, but first we triggered a crash using the proxy in this case, and we reach Android Telecom. This triggers the crash. There is a period between triggering the crash and rebooting the phone. In this tiny window, we trigger the second bug, which is unzipping and traversing the path and dropping file on SD card. OK, it works fine. I don't know why, but it works. Who cares? All right, so we reboot the phone. And when the phone reboots, we have a file on the SD card. Great. Galaxy Apps will pick up this file and reconfigure itself based on this file. It will then schedule automatic update checks. And the way they do it is using Android Job Scheduler. Android Job Scheduler is the OS built-in mechanism for scheduling periodic jobs. But it was changed. The behavior behavior was changed in Nougat to prevent uneducated developers from misusing it. So they realized some developers didn't know how to use the API, and they were draining the battery way too fast by specifying a very short period of time when jobs should occur. And they use clamping to bump up the time to at least 5 minutes. It doesn't work for us because, to at least 15 minutes. It doesn't work for us because we have only 5 minutes to do this at Pwnie. There is a trivial integer overflow in the implementation. I'm running out of time, but it's not an interesting bug. It's just a way to circumvent the protection. It's not a security mitigation in any way. It's just there to protect against, as I said, uneducated devs. And this is what happens. We schedule the update check, and now we intercept all of the traffic between the phone and the Samsung servers. We use MITM proxy to intercept this traffic. This is what the update process looks like. The phone will issue a get update list command. We intercept this. And what this looks like is a complete list of every single application on the phone and each version corresponding to this application. This reaches the server replies with the latest version available for each one of the apps. To make sure the phone will request further information, we bump up the version. Remember, we're man in the middle in the traffic. We bump up the version. This reaches the phone. The phone will then request further information. The response for this further information request will contain a GUID. This GUID is later on passed to the package manager when they perform the installation. So we change this to a GUID of the package that will correspond to Traversale in this case. They will then issue a final request that will ask for the URL where to download this package. So we change this back to the original name because it reaches Samsung server, and we don't want Samsung server to get confused. Samsung server will then reply with information for the Samsung package. But we change the URL, and we change the signature. That there is the signature that will be used to compare the APK signature when installing the application. All right, at this point, we're installing an application, but we don't have any permissions. Well, the way it works is, if you want to do something sensitive on the phone, you prompt the user to confirm the permission first. So at least this is how it works since SDK 18, or Android Jelly Bean. The problem is that if you specify an SDK with a much lower version, this prompt is just skipped because Android is trying to implement some sort of backward compatibility, and they don't want to break apps. OK, so now we have all of the permissions we want. We chat to ZDI, and we're like, we have this app installed. We have all the permissions. Is that enough? Not really. You need to demonstrate codecs that can exfiltrate some data. The app is placed in what they call a stopped state. And the way we wake up the app is by finding another bug and exploiting it. This other bug is in the contacts provider, modified by Samsung for some reason, to listen for package changes. So as soon as we install a package, the contacts provider will be notified by this change, and it will act on it. It will take the package name, take the manifest for this package, and look for content providers implemented by this package where the metadata is something related to a contact directory. So if we modify the Traversale manifest, which is the manifest of the malicious app we're about to install, we can implement a content provider. And when we implement the query method for the content provider, this is the code that will be executed by the contacts provider when searching for information in our application. So at this point, we instantiate Traversale. This is what the whole thing looks like. I don't have time to go through everything to recap, but it's actually quite unlikely to work from the first time, and it actually did. I have no idea how. And I'm sorry, I don't have time for the demo, but the whole thing is just ridiculous from a victim's point of view, because you open your browser, you see your browser switching to another browser, then you see this browser downloading a file, then you see your phone crashing, then the phone comes up, and an application is getting installed. Yeah, unfortunately, not enough time to go through this. Not the most realistic exploit. I mean, not realistic in a real-world scenario, but it's a hilarious one, especially for Pwnie. Unfortunately, we have to stop the demo. Conclusions. Well, apparently, Samsung is doing something very, very wrong. Android is not a terrible operating system. It's actually quite all right. But OEMs like Samsung, Xiaomi, Huawei, other kind of friends, they ruin the operating system by installing tons of bloatware on it and exposing so much attack surface unnecessarily. Take away from this, do your best to automate some aspects of your bug hunting routine without investing too much time on it. Come up with a plan on how much time you want to spend on automation and actual bug hunting. And when you find bugs, especially logic bugs, don't throw them away. I mean, we found the phone reboot issue way before we had an idea about the chain. But instead of discarding it, I just stashed it. And when we got stuck, I went back to my stash. I'm like, wait a second, we need to reboot the phone. I got this absolutely useless reboot from a few months ago. Maybe we should just use it. And last but not least, Android is a complete nightmare in terms of IPC variety. So applications on the phone have so many ways to talk to each other. We have content providers, file providers, broadcast receivers, and activities, and implicit and explicit intents. There are so many ways to talk to each other and exchange information. And the more channels available, the more channels you have for applications to talk to each other, the more attack surface exposed. And it's really easy to fuck it up. So when you review an application or something like that, you need to make sure that the attack surface exposed is as minimal as possible. Otherwise, bad things can happen, as demonstrated just now. And I think that's it from me for today. Are there any questions?